Hello. In this video, we're going to be taking a look at the notes for AP Physics C, Unit 3, Conservation of Energy. Remember to pause or rewind the video as necessary. Let's take a look. Review of energy concepts. Well, the main physics equation for work is force times distance times the cosine of the angle, where angle, theta, is the angle between the force and the displacement. Work is the change in some energy. It's also a force acting through a distance. The unit of energy is the joule. The kinetic energy equation is 1/2 mv squared. The gravitational potential energy is U sub g equals m times g times h. Force applied by a spring is k, the spring constant, times x, the distance you stretch or compress the spring. The spring potential energy, U sub s, is equal to 1/2 times k times x squared. And then the energy lost due to friction is the work done by friction, which is the force of friction times the distance. Energy can be lost when kinetic friction is acting. What is mechanical energy? Well, it's the sum of kinetic and potential at every point. The law of conservation of energy states that the total energy from all forms remains constant. Now, this is true when no external forces are acting on the system. The conservation of energy equation is energy total equals energy total. E initial equals E final, where E is the total energy. And you can expand it to K plus U equals K plus U, and we would write the energy lost due to mechanical energy on the final side if indeed there is mechanical energy lost due to something like friction per se. When should conservation of energy be used? Well, if you're given, let's say, velocity, height, and a spring, you must have two of these three changes in order to apply. So in other words, a change in velocity and a change in height, or a change in velocity and a change in spring stretch, or a change in position and a change in spring stretch. There must be two of those three variable changes to have two of those three changes in energy to make conservation of energy applicable. Newton's laws should be used when you're finding a force or acceleration given a mass. Power is the rate at which energy is used. The units are the watts, capital W, or joules per second. It's the energy per unit time, or the energy divided by time, which could also be written as the work divided by time. Since work is force times distance, it's force times distance over time, and force times distance over time is velocity. It could also be written as force times velocity. Okay, now the dot product is a mathematical way of multiplying vectors. In fact, there's two ways to multiply vector quantities. One is through what is called a dot product or a scalar product, and the other is through a cross product or vector product. And at this level of math, you start to see dot products and cross products used occasionally in college level math and college level physics. We don't need to use dot products and cross products that much in what we do, but it's good to introduce it to you so that you are familiar with it when you head into university level work. The dot product, also known as the inner or scalar product, is a way of multiplying two vectors. Now, specifically, it's when you multiply two vectors and your product is a scalar itself. In a physics example, that would be a lot like finding the work. Work is equal to force dot displacement. Both of those are vectors. However, the vector quantity, the two vectors must be going the same way. They must be going parallel. So you need a parallel component of the force times the displacement in order to do any kind of work. So the product of those two will end up being a scalar and not a vector. Work is a scalar. Energy is a scalar, not a vector. Mathematically, how do we actually compute a dot product? It's very, very easy. So say, for instance, we have a vector notation given like a in the a sub x in the I direction plus a sub y in the j direction plus a sub z in the k direction. Remember, the ijk unit vectors just tell you the x, y, z direction of the vectors. That's all. And then you've got some b vector, bx, by, bz, a dot b. And that's how you would say it. A vector dot b vector, just say a dot b. Well, a dot b can be expressed as ax times bx plus ay times by plus ay az times bz. So you would just literally multiply the components of each one and then add them all together. Another way we could do it is by taking the magnitude of a, what the amount of a is, times the amount of b, times the cosine of the angle. That ought to look pretty familiar in terms of what we had with an equation right here, because the equation for work was force times distance times the cosine of the angle. A dot b could also be represented as and again, we're just putting absolute value bars because it's the magnitude. So when we say the absolute value of vector A, we're saying the magnitude of vector A. So the magnitude of vector A times the parallel component of the magnitude of vector B, or the parallel component of the magnitude of vector A times the magnitude of vector B. So either one of those would work. You can see them, the picture oriented over on the right here. So vector A points this way, vector B points that way. And so what I would need is, in order to get, I need them to go the same way. So A is already going this way, and B has parallel and perpendicular components. You would need the parallel component of B times A to get the dot product of those two vectors. And then, or similarly, you could go the vector B, the magnitude of vector B, times the parallel component of vector A that's pointing in the same direction as B. Let's take a look at this energy review. We have a block that's dropped from a height above the floor. The block glides until it reaches a smooth, frictionless track until it reaches the floor at point A, where the track curves and projects the block at initial angle theta to the horizontal. Write expressions for, well, in part A, we want to write an expression for the velocity when it reaches the ground. So this part A is going to be straight conservation of energy. Why? Because when it's falling, there's no external forces acting on this. Therefore, the total energy you start with at this point is the total energy end with at that point. Let's examine the energies. Well, the kinetic energy is going to be 0 to start with because we're releasing the block from rest. The gravitational potential energy is mgh, which means the total energy, which is the sum of those two, is just mgh to start with. At point A at the bottom, the kinetic energy at point A is 1/2 mv squared. We write the equation for kinetic energy if we have it. The potential energy, the gravitational u sub g at point A, is going to be 0. That's the lowest point of the problem. Okay, you can't get any lower than the lowest point of the problem. And if we add those together, the total energy at point A would just be due to the kinetic energy there. So the conservation of energy equation is total energy initial equals total energy final, or mgh equals 1/2 mv squared. Now we have to solve this equation for v. So in order to do that, we have to multiply by 2, divide by mass, and then square root. And we get the square root of 2 times g times h. The velocity when the block reaches the highest point B. Well, normally I would say if you knew what this height was, you could use conservation of energy again. Because at point B, you do have kinetic energy at point B, 1/2 mv squared, I'm going to say vb squared, and then the potential energy at B would be mgh B, which means the total energy is the sum of those two, right? But we don't know this height right here, so since we don't know the speed and we don't know the height, you don't know two things, that becomes not very helpful for using conservation of energy to find the speed. So we're going to have to find the speed over the top a different way. And here's how we can do it. We've got the block is being launched as a projectile right here. And you might remember that the projectile, if I draw an arrow here to represent V naught flying off the edge of that ramp, you might remember that there is a V naught in the X direction and a V naught in the Y direction. Now Vy goes to 0 at the top here, but Vx stays constant the entire time, all the way, even at the top. So V at the top, that's the same as V naught X. And we'll go ahead and write that. So V at point B is the same as what V naught X is, which is the same as V sub A times the cosine of the angle. Now you already have a variable, you already have a value for V sub A. V sub A is the square root of 2gh. So all I'm going to do is substitute that square root of 2gh for V sub A. And it's the square root of 2 times g times h times the cosine of the angle. Okay, the maximum height h that the block reaches while it's a projectile, now we can use conservation of energy because now we have a value for V sub B, which is this right here, and we could use that to solve for h, the height. So we're going to use conservation of energy again, which again tells us as an equation, total energy initial equals total energy final. The total energy initial, now here's the way you can do this. You can start from the top and go to point B, or you can start at point A and go to point B. Your initial point can be anywhere you have information. I'm going to choose to start at the very, very top again and just skip A altogether. I'm going to go from here directly to here. So my initial energy was mgh. My final energy is mgh sub B plus 1/2 mvb squared. There you go. And I'm going to zoom in on this so we can see it a little better. First of all, this was mgh, capital H, equals mg little h plus 1/2 mvb squared. And you're solving this equation for little h. So in order to do that, you're going to have to subtract this over to this side and then divide by so I think one of the first things we can do, I'm going to go ahead and multiply by 2 just to kind of get rid of the fractions everywhere. And when I do that, I get 2 mgh equals 2 mg little h plus mvb squared. We can divide by m on all three parts. And you can see the mass cancels everywhere. And now we have 2gh equals 2g little h plus vb squared. Okay, now you are trying to solve for little h, so what I'm going to do is I'm going to do a little bit of substitution here, okay? We know VB is the square root of 2gh over, or times cosine theta. VB squared, which is what I have to substitute for, well, I'm going to square all that. VB squared would be 2GH times cosine squared theta. So I'm going to substitute for that. We have 2GH equals 2G little h plus 2G big H cosine squared theta. And now we're going to go ahead and solve this thing for little h. We can do that by taking this term and subtracting it over to the left-hand side. 2GH minus 2GH times cosine squared theta equals 2G little h. You'll notice that 2G is a common thing to everything, right? So I'm going to go ahead and divide out a 2G by all three terms and really just kind of pare down this equation a little bit, make it easier to solve. And then I'm going to factor out an h term here. So if I do that, I get h times the quantity of 1 minus cosine squared theta equals little h. Okay, well, I'm almost done. If you remember your Pythagorean identities, sine squared plus cosine squared theta equals 1. So if I solve for sine squared theta, I'd be subtracting cosine squared theta from both sides. So sine squared theta is actually 1 minus cosine squared theta. And we're going to make that substitution right there. So this becomes h is equal to big H times sine squared theta. In this example, we have a block is released from height h above the ground on a smooth, frictionless track. The block glides down the track to a vertical loop of radius r is shown. What minimum value of h must be the block dropped in order to successfully complete the loop without losing contact with the track? So this last phrase right here tells you that when you go over the top, the normal force goes to 0 at the top. Now, if we're talking the normal force going to 0 at the top, that's telling you that we're going to be using centripetal forces in this problem. Okay. Now, since the block is undergoing a change of height, change in speed, and conservation of energy, this is a two-part problem where we're using not only conservation of energy, but centripetal forces as well. So first thing I'm going to do is I'm going to find the speed at the top of that loop, and we're going to use centripetal force to do it. So the forces at the top, if we looked at the roller coaster, if I draw the cart at the top of the loop right there, the forces at the top would be it would just be the weight. It would just be the weight mg, because there is no normal force, because if we're talking about just making it over the loop without losing contact with the surface, that means the normal force have effectively gone negligible. It's gone to 0. So if it was going fast enough, we'd have normal force going into the circle as well. So this means the net centripetal force, right, is equal to mv squared over r. Well, the net centripetal force in this case is mg, the weight. So we have mg equals mv squared over r. Masses cancel, and if you multiply by r, we can see that v squared is equal to g times r. Okay, that would be, and I'm going to call this right here point B, and I'm going to call the minimum height that I need to release it from height A. Or I will just height, just where we release it from here, that is going to be point A. So this would be VB squared. Now we can go ahead and use kinetic energy to work the solution to the problem. Okay. We know at the top you're releasing it from rest, so we have no kinetic energy. Your potential energy, though, is going to be m times g times big H. At the top of the loop, you have kinetic energy going over the top, 1/2 mvb squared, and you have gravitational potential energy of mgh, where at this point right here, h is equal to 2 times r. Radius plus radius, right, is h, or 2 radius. So that would actually be equal to 2 mgr. Should probably write it like that. Okay, so making the substitution, initial energy equals final energy would be mg big H equals 2 mgr plus 1/2 mvb squared. Now what I'm going to do is I'm going to substitute the value for vb squared is gr. I'm going to substitute that right here. And we have mgh is equal to 2 mgr plus 1/2 m times gr. Well, that's going to be mgh equals 2 mgr plus 1/2 mgr. Well, 2 plus a half, you can see, oh, sorry, I didn't write it that way, mgr. 2 plus a half is 2.5 or 5 halves. So we would have mg big H equals 5 halves mg little r. You can see the masses and the g's are going to cancel. And h is 2.5 times the radius. That's where you need to release it from. Okay, now in this next problem, we have a block sliding down a rough incline. Okay, so there's going to be some friction on this incline. It's going to compress a spring, and when it's fully compressed, it's going to stop for an instant. So we have conservation of energy written all over this, but we have also the loss due to mechanical energy as well. So let's see how that plays out. Conservation of energy is in this problem. Why? Change of height, change in speed. Right? That's the recipe for telling how to use it. So initially, your initial energies, initial kinetic energy, 0, starting from rest. Your initial gravitational potential energy is going to be mgh, and your initial spring potential energy is going to be 0 because the spring is not compressed yet. If I look at energy final, which is the energy right here when the spring is fully compressed, then your block comes to rest, so kinetic energy final is 0. Your gravitational potential energy is 0 because you're at the lowest point. You're not going to go any lower than the lowest point. And your spring potential energy is 1/2 kx squared. So the equation for this, we're trying to determine the distance d, distance x that the spring gets compressed. Well, initial energy equals final energy, and the initial energy was mgh, and that's going to be equal to 1/2 kx squared plus the work done by friction. That right there is accounting for the loss in mechanical energy that you're going to have as you're sliding down the hill. Okay, now at this point, there's going to be just a lot of substitution and a lot of tiny little algebra steps along the way. Okay, so the first thing we're going to do is we're going to break this into an actual triangle where the distance that it fell, this whole distance from here to here, is not just d, it's d plus x. Because d is the distance it slides until it hits the spring, and then x is the distance you compress the spring. So d plus x is the total distance it slides until it comes to rest. If that's the hypotenuse of the triangle, that makes this side d plus x times the sine of the angle, and that makes this side d plus x times the cosine of the angle. And that's what we're going to do at this point, is we're really just going to be making some substitutions for various points along the way. So my first substitution is for height. The height is going to be that value right there, d plus x times sine theta. So what I'm going to do is I'm going to rewrite this as mg, but then times the height would be d plus x sine theta. That's going to equal the 1/2 kx squared, that's already there. And we're also going to substitute for the work done by friction. Well, friction, the work done by friction is equal to the friction force times the distance you slide it. And friction, just so that we can follow the substitution here, friction is equal to mu times the normal force times the distance. So as we go back and review the picture and the forces acting on this thing, you have the weight going down this way, you've got the normal force going this way, and opposite the normal force, you'll remember you have mg cosine of the angle. So mg cosine of the angle balances the normal force. Normal force is mg cosine. Okay, so let's make that substitution right there. So plus, we'll say friction times distance. But friction times distance, what is the distance? It's going to be d plus x, not just d. Okay, let's go ahead and substitute. Well, we're going to do a couple things, actually. We're going to go ahead and substitute for friction, and then we're going to distribute mg and sine theta through parentheses there. So what that becomes is that becomes mg... actually, let me just take care of this substitution first, not do too many steps at one time. So mg d plus x sine theta equals 1/2 kx squared plus, now friction is mu times normal force, so we're going to go mu times mg cosine theta, we're substituting for normal force, times the distance, which is d plus x. Okay, so now, and I guess I'll write that this way too. So mg sine theta times d plus x. So what we got to do now is we got to distribute. And this becomes mg d sine theta plus mg x sine theta equals 1/2 kx squared plus mu mg d cosine theta plus mu mg x cosine theta. Okay, so now at this point, you're going to bring the kind of the terms together. The whole point is to solve for x. So what I'm going to do is I'm going to take this term here and I'm going to subtract it so that I can subtract it from that term right there. And then I'm going to take this term over here. Take this term over here, and I'm going to subtract it from that term right there. All right, and there's a reason why I'm going to set it up this way. if I do that, I have 0 on the left side equals 1/2 kx squared plus, now initially I have mu, I'm going to start with the x term over here, so mu mgx cosine of the angle minus mgx sine of the angle plus mu mgd cosine of the angle minus mg, let me see. Oh, yes, minus mgd sine of the angle. There we go. Okay, and so now what I'm going to end up doing is I'm going to factor out a few things just to make this a little easier. So this is going to be 0 equals, we have 1/2 kx squared plus, you'll notice that the common thing to this is essentially mgx. I'm going to factor out an mgx. Oh, really just, yeah, I'm going to factor out an mgx, the whole thing. So mg, and then inside I have mu cosine of the angle minus sine of the angle times x, plus I'm going to factor out an mgd here, and I'm left with mu cosine minus the sine. Okay, and why am I doing this? Because I'm setting up a quadratic equation where this is A, this is, all of this is my B term, and all of this is my C term, and we can throw that into quadratic equation. So now at this point, we can substitute for the values given. So for instance, the A term, this would be the A term, this would all be the B term, and this would all be the C term. So we can figure out what those are. And I'll again, keep this set equal to 0. And I want to do that again because I'm trying to set it up like a quadratic equation where I have A term, B term, C term, and I can then throw that into quadratic formula. So we were told that K is 120, mu is 0.25, and theta is 37, and the mass is 5. So I'm going to use that information to plug in. So we've got 1/2 of 120 x squared plus mg would be 50, 5 times 10, times this whole part right here, mu cosine theta, so 0.25 cosine 37 minus sine 37, right? There's your B component. And then the last part right here is you got the mgd part, so 50 times, what was the distance? Distance was 10 meters. So 50 times 10 is 500, right? And then we're going to multiply that times 0.25 cosine 37 minus sine 37. Okay, so throwing this in one more time, we have 60 x squared. Let's see, now this whole term right here, this is going to give you a negative value. So minus about 20.1 is what that simplifies to. And then this whole thing right here simplifies to about 201. So there's your A, there's your B, there's your C. Throw it into quadratic formula. So quadratic formula says x is equal to negative times negative 20.1 plus or minus the square root of 20.1 squared minus 4 times A, which is 60, times C, which is negative 201. All over 2 times 60. Well, the negative cancel, leaving you with 20.1 plus or minus the square root right? If we do this part right here, negative negative is positive, and if we go 20.1 squared plus the 4 times 60 times 201, right, and then take the square root of that, get approximately 220.55, roughly. And then on the bottom, 2 times 60 is 120. So you have two possible answers that work here. So we have x is equal to, if we go 20.1 plus the 220.55 divided by that, and we get 2.01 meters, right? And then if you go 20.1 minus, you get a negative answer. So negative 1.67 meters. Can't be negative. 2.01 meters is how far it compresses before it actually comes to rest. In the next example, we have a bungee jumper of mass 100 kilograms jumps off a bridge. His cord has an unstretched length of 20 meters and the spring constant of 20 newtons per meter. Determine each of the following. Assume that the man does not strike the ground. So let's take a look at this being the initial energy right here. We have no kinetic energy to start with. The gravitational potential energy is mgh, because you have the potential to fall from up there, and the spring potential energy is 0 because the bungee cord is not stretched yet. So if I wanted to determine the man's speed just as the cord is beginning to stretch, we're talking about right here at point A, that means the cord has not stretched yet. So what happens at, we'll call this, I guess, point A. The energy at point A would be, you now have kinetic energy, so 1/2 mv squared. We can call this the lowest point in the problem. We can call this potential energy equals 0. And we haven't stretched the spring yet, so no spring potential energy either. So what we end up with is the initial energy equals the final energy, which means mgh at the highest point is 1/2 mv squared at the lowest point. Multiply by 2, divide by mass, square root. V is the square root of 2gh, or 2 times 10 times h, which is 20. Well, 2 times 10 is 20, times 20 is 400, square root of which is 20 meters per second. So we're looking at 20 meters per second before the bungee cord even begins to stretch. Now, in part B, it says, how far has it fallen when his speed is maximized? Okay, speed is going to be maximized when acceleration goes to 0. Now, this happens when net force is 0, or I should say when forces are balanced. So if we look at part B right here, the force, we have the weight going up, and we have kx, the spring force equals kx going up. And so we balance those, and we have forces up equal forces down, which means kx equals mg, where x is the distance you stretch it, right? So that's going to be mg over k. So we've got 100 kilograms times 10 over k, which is 20 newtons per meter. And 1,000 over 20 would be x equals 50 meters. Now, that's not how far the man has fallen. The man has fallen the 50 meters plus the actual length of the rope. Because remember, the man builds up speed of 20 meters until the actual bungee cord begins to stretch. So you got the 20 meters of bungee cord plus the 50 meters of stretch. So the man actually falls 70 total meters before the speed is actually maximized and the acceleration drops to 0. Find the actual man's maximum speed during the fall. Okay, so again, we're going to be using conservation of energy. So the initial energy, the kinetic energy at the top was 0. The potential energy at the top was mgh, and the spring potential energy was 0. The final energy, which I guess I'll write it over here, the final energy, that would be at the point where maximum speed is happening. You have kinetic energy, so we have 1/2 mv squared. You are stretching the bungee cord, so we have spring potential energy is 1/2 kx squared. But if you remember, we treated that point, you don't really have the ability to fall at that point. And so what we end up with is mgh equals 1/2 kx squared plus 1/2 mv squared. Now to solve for speed, I'm going to go ahead and start by multiplying everything by 2 so I can get rid of the fractions. Fractions don't need to be there. So we get 2 mgh equals kx squared plus mv squared. We can divide by mass, and I can subtract this. So take this and subtract it, and then divide by mass. And I get that the speed is equal to 2 mgh minus kx squared all over the mass. And that's what I'm plugging into. So 2 times 100 times 10 times 70, because that's how far we've fallen before the speed is maximized, minus k, which is 20, times the fact that the spring stretched 50 meters, and I have to square that, over the mass of 100. Take a second to plug that in your calculator. If you do that correctly, you should get in the neighborhood of about 30 meters per second. Determine the distance the man has fallen. Okay. Before, when he comes to rest. So again, I'm going to use the initial point of energy as the very, very top. So kinetic energy is 0. Gravitational potential energy is mgh. The final energy, the kinetic energy comes to 0 again. The gravitational potential energy, there is none. And the spring potential energy is going to be 1/2 k, but the x squared, it's 1/2 kx squared, but the x, this is where it's different. X at this point is going to be h minus L. Okay, let's think about that. Go back to the picture. We have the point where it is fully stretching. You've got the full height right here minus the original length of string here. Okay, that's what the full stretch is. So the full height that you fall from minus the original length is going to be x, the distance you stretch the bungee cord. So I'm going to write that as h minus L squared. So we have mgh is the initial energy equals 1/2 k times h minus L quantity squared. Well, that's going to be mgh equals 1/2 k, and I'm going to expand that binomial squared, and that becomes h squared minus 2hl plus L squared. And then I'm going to distribute that into all three terms. So mgh equals 1/2 kh squared minus 1/2 k times 2hl plus 1/2 k L squared. Okay, well, this becomes mgh equals 1/2 kh squared minus khl plus 1/2 kl squared. I'm going to go ahead and subtract the mgh over to this side here. Again, I'm creating a quadratic equation, okay, because I'm solving for the distance the men have fallen from. I'm solving for h. So I notice I've got an h squared, I've got an h term, right? I'm going to set this up as a quadratic equation. So 0 is equal to 1/2 k h squared, and then minus my two h terms would be khl minus mgh, there's my h term, plus 1/2 kl squared. And what I'm going to do is I'm going to factor out the h in this term right here. So let me rewrite that as minus, and if I factor that out, we've got kl plus mg times h. There's the factor term. So there's your a, there's your b, and this whole last thing is your c. Okay, which would become 10, because half of 20 is 10, so we have 10h squared, okay, minus this whole bit right here is becomes 1400 when you put that in, right? Make sure you practice putting this in yourself. Don't just rely on what I'm giving you. Okay, plus, and then 1/2 kl squared ends up being about 4,000. There's your c term, there's your b term, there's your a term. That's all set equal to 0. H is equal to negative times negative 1400, whoops, not 14,000, 1400, plus or minus the square root of 1400 squared minus 4 times 10 times 4,000, all over 2 times 10. And you're going to get two possibilities. You'll either get 137 meters or you're going to get 2.9 meters. Now, it obviously didn't drop that far, so 137 meters is the total height that it fell from. Make sure you practice doing that part yourself independently so that you can do my steps that I kind of went through a little bit quickly yourself independently. Part E, explain qualitatively the man's motion over a long period of time. Well, over a long period of time, the man is going to bounce and oscillate up and down on the cord. Part F, determine how far below the bridge the man is when he finally comes to rest. Well, he comes to rest at a point where his weight balances the spring force, so that was the point that we actually found right here where you're not accelerating. So where you're not accelerating, originally we were moving through that point with maximum speed, but over time when the oscillation stops and he comes to rest, he will come to rest at 70 meters below where he started from. work as a dot product of the work energy theorem. So work done by a constant force is force dot x. Positive work is done when the angle between force and displacement is acute, meaning less than 90 degrees. Work energy theorem tells you the net work is equal to a change of object's change in kinetic energy. And this is kind of the shorthand way to write it. Now, let's go ahead and introduce something called the integral or the anti-differentiation. So the operation that is the inverse of the derivative is called the integral, whereas the derivative is used to find slope, the integral is used to find the area under the function, okay? And how it's done, we split the axes into tiny little pieces. So we take this and we split it into tiny little pieces, each one called dx, small little tiny value of the x-axis. We multiply dx by the value of the function, meaning the height, and you create an infinite number of really skinny rectangles under the curve that we can then approximate the area of. And if we make dx infinitely skinny, that means we can have an infinite number of rectangles underneath the curve, which means we can approximate it very, very well. And we get dA, the differential area, is equal to the value of the function, the height, times the width. Add up all these infinite number of tiny rectangles, and we get the area under the function is equal to the integral. So the integral is drawn as this symbol here that kind of looks like an elongated S, and that really is a symbol there to stand for sum, because you're summing up an infinite number of these little tiny skinny rectangles. But that symbol is called the integrand. So this is the integral symbol. That little part right there is called the integrand, right? And that's the differential. All the differential really tells you is what variable you're taking the integral with respect to, in this case, x. There's two types of integrals. There's an indefinite integral, in which case when we answer the problem, we have to essentially add a constant. Now, why would that be? Well, remember, integration is the opposite of differentiation, the opposite of derivatives. So if you have, let's say, just to give you an example, let's say we had f of x equals 2x plus 3, and I asked you to derive that. Well, f prime of x would just be 2, because the derivative of 2x is 2 and the derivative of 3 is 0. Now, if you go backwards and you integrate 2 with respect to x, well, you get 2x, right? You go backwards, but the problem is plus what? You originally had a constant, didn't you? So plus a constant just adds the possibility of there being a constant there in the first place. And you have to be given some sort of initial values in order to figure out what the actual value of that constant would be. Now, a definite integral means that you put what are called limits of integration. And the way you evaluate it is you take your integral function that you go and you evaluate the upper limit of integration in place of x, and then minus the lower limit of integration evaluated with x. This is known as the fundamental theorem of calculus, where a and b are limits of integration, and f of x is the antiderivative of x. If we want to evaluate the integral of negative 1/4 x squared plus 4x minus 7 from 4 to 16, we're going to need to use what's called the general power rule formula for integration. Let me remind you what that is. General power rule states that if we have an integral going from a to b of some function f of x dx, okay, and that function f of x dx is x to the n power, meaning some polynomial, then this gets evaluated. What we do is we add 1 to the exponent of the, so it becomes n plus 1, and then we take whatever that new exponent is and we divide by that new exponent. So we could raise to a power of 1 and then divide by that same new exponent. And we're going to evaluate this from a to b. Okay, so here's how we would do this. The integral of this function would be broken down into -1/4 x to the 3 over 3 plus 4 x to the 2 over 2, because it's already x to the first power, and then minus 7x. And you have to evaluate that from 4 to 16. Okay, so now what is this going to look like? We're going to break this down into larger segments. So the first segment is going to be, first of all, -1/12 times 16 to the third power plus 2 times 16 squared minus 7 times 16. All of that, and then Scott's going to get subtracted from -1/12, 4 to the third power, plus 2 times 4 squared minus 7 times 4. Okay, cleaning this up a little bit, this would give us about -341.3 plus about 512 minus 112 minus, and then over here we have negative about 5.3 plus 32 minus 28. Okay, so that would be 58.7 minus a minus 13, which is 60. Basically, it's approximately 60. And if you look, take a look at the area. Look at the shaded area in this here. The function is this quadratic, okay? That quadratic function right there. And we're finding the area that's bound between the curve here. Now that goes from x equals 4 to 5, 6, 7, 8, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 to this point right here. But then 15 and 16, so we take basically this positive area and we subtract from it that negative area. And if you take this minus this, what do you know? You get 60 as well. Work as an integral. The expression for work as an integral would be, and this would be what's called a work done by a variable force, as opposed to a constant force. And that's really easy to tell. Instead of given a force value of something newtons, you're given a force function, a function of force as a function of distance. So work is the integral from x initial to x final of our force function, our force is a function of x, dx. Again, we use this when force depends on position, a variable force function. We can only use the dot product. Remember, the dot product was the exact same as work is equal to force times distance times cosine of theta. We can only use this when the force is a constant value. Okay, same force applied everywhere. We can only use work equals F of x if force is constant and force is parallel to displacement. Let's go ahead and differentiate between conservative and non-conservative forces. A conservative force is one with a potential energy associated with it, such as gravitational or spring forces. Well, those have gravitational potential energies, therefore, those are representative of conservative forces. Conservative forces are also ones where the work done by the force only depends on the starting and ending positions, not the path between the starting and ending positions. And then finally, a conservative force is one in which the work done is equal to the opposite of that change in potential energy. So an example of the last one, the work done by gravity as you lift something upwards, okay? Now keep in mind, that's going to be a negative force times distance, or a negative work, basically, because the gravity goes down and you're displacing it upwards. However, when you move it upwards, you're increasing your potential energy, right? And that's a positive change in potential energy. So this is an example where the change in potential energy is equal to the negative work done by gravity. A non-conservative force is one that does not have a potential energy associated with it. Friction, tension, normal force, even applied forces. It's also one in which the work done depends on the path you take. Friction is the most obvious culprit of that. Two expressions for relating potential energy as a conservative force. Well, if work equals the integral of f of x dx, then that means the potential energy is equal to a negative f of x dx, where f is a force, because we established, remember, that work is equal to a negative change in gravitational potential energy, at least for a conservative force, right? Now, if we take the derivative of both sides of this equation here, the derivative of delta u is just du, and the derivative itself cancels the integral, and we're left with f negative f of x dx. And if you solve for f is equal to the negative derivative of the potential energy function related to position. So we have a way of getting the force function from the potential energy function and the potential energy function from the force function. So I would put a box around both of these. They're both very useful. Okay, now we're going to use a little bit of integration to show where these formulas come from. Let's show how this conservative force becomes that potential energy, spring potential energy. Here we go. Okay, we're going to use the equation U, the potential energy, is equal to the negative of the force function dx, and I could write it like this. I could write it U of x is equal to the negative of the force function dx. And what I would do is I'm going to do this from 0 to x, meaning from not stretching the spring at all to some random stretch, any stretch. Okay, then what I'm going to do is I'm going to replace that with my function for the spring force. So we get u of x is equal to the integral, the negative of the integral of negative kx dx. Okay, so now this is a constant, so we can kind of bring this outside. And so now the u of x function, which at this point we'll just call it u. We'll just call it u. U is equal to negative times negative k times the integral of x dx. Now keep in mind that's x to the first power, right? So those are going to cancel. And that's going to be k times, and this was from 0 to x, we're going to go x to the second power over 2. Remember the power rule. We got to add 1, right? And then divide by 1 plus 1. Okay, and we're going to evaluate this from 0 to x. So u equals k, and I'm going to be plugging in x, well, for x, which that's easy, x for x is just x. Then I'm going to be plugging 0 in for x. So kx squared over 2 minus k times 0 squared over 2. Well, that whole thing goes to 0. And so what we end up with u equals 1/2 kx squared. Show how F equals negative mg becomes that potential energy, gravitational potential energy, mgx. Again, we can start off with the exact same equation. U equals negative of the f function dx. Now this time I'm going to go from 0 to h, where h is my x, my distance direction. U is going to be equal to the integral from 0 to h of negative mg dx. Well, m and g are constants, so bring both of those out front, and u is now equal to negative times negative, which is mg, times the integral from 0 to h of 1 dx. And the integral of 1 is just x. And then we just slap on the mg scalar multiple out front and evaluate that from 0 to h. This becomes mg h minus mg 0, which cancels, and u equals mg h. Now, since we wanted to show that it becomes mgx, I guess what we should have done is we should have evaluated this from 0 to x, and when we plug x in for x, we get mgx. Show that net force equals ma becomes the kinetic energy equation. So, and for that one, we're going to use the work equation. So work is equal to the force function dx, and we're going to evaluate this from 0 to v. Now that seems kind of weird because we're integrating with respect to x, right? Well, just watch. We're going to limit this from 0 to v, velocity v of ma. So we're going to replace ma with the net force, dx. Then what we're going to do is we're going to substitute for a, and here's how we're going to do that. Mass is a constant, by the way, so we'll bring mass out front, and a is dv dt. It's the derivative velocity with respect to time times dx. Now what I'm going to do is I'm just going to reorder this. I could take this and simply swap their order. And I actually get the work is equal to the mass evaluated from 0 to v of dx over dt times dv. All I did was just swap those. Now, what is dx over dt? That would be the mass evaluated from 0 to v of v. That's velocity. So we're integrating velocity with respect to velocity, and it's v to the first power. So what do we get? m. And then this would be, if we evaluate the integral, it's going to be v to the 1 plus 1 over 1 plus 1, evaluated from 0 to v, which is mv squared over 2 from 0 to v, which is m times v squared over 2 minus m times 0 squared over 2, which the second part, of course, cancels. And mv squared over 2, you guys should be able to see that. That would be the kinetic energy. And work equals a change in kinetic energy. That's work kinetic energy theorem. Consider a force acting on a particle. The force f of x depends on the position of the function. Let the object travel from xa, which is way over here, to xb along this particular path at all times under the influence of f of x. Let's see. Work is given by the path integral, which is the integral taken between the path p that the object travels from A to B. Split the path into tiny steps. So notice we're splitting it into tiny rise over runs, little tiny steps. And little tiny pathways all along. This then becomes the integral of the force function, dx, from A to B. So for a conservative force, the path integral to evaluate this, we have negative change in potential energy is going to be the u function evaluated at x of A minus the u function evaluated at x of B. Potential energy functions. Stable equilibrium is the minimum potential energy function, so that the object will be placed at stable equilibrium, will stay there, will not go away if slightly offset from equilibrium, as opposed to unstable equilibrium, which is a maximum. So this is a minimum in the potential energy function. That's a maximum in the potential energy function. All right, let's take a look at this example. We have a particle of 2 kilograms, has the potential energy function u of x equals 3 times the quantity x minus 1 minus the quantity x minus 3 cubed, where x is in meters and u is in joules. The following is a graph of the potential energy function. Okay. So the energies indicated on the vertical axis are evenly spaced so that E3 minus E2 is the same as E2 minus E1 and so forth. The energy E1 is the potential energy function U evaluated at x1. So we can see x1 right here. We go up to the U function, which is U of x, and we evaluated it right there. So E1 is the potential energy function evaluated at that x1, and so forth. E3, for instance, E3 would be the potential energy function evaluated at 1/2 x1. E2, you could probably figure that out. E2 would be evaluated somewhere right here, and right here. E3 would also be evaluated right here at x3. Okay. And the energy E3 is evaluated at x3. So to find the max or min, so check this out, ladies and gentlemen, to find the max or min this or this, we essentially need to find where the slope of this graph equals 0. In other words, we're going to take the derivative of this function and set it equal to 0. So that's what we're going to do. We're going to have the original u function, so we have u of x is equal to 3 times the quantity x minus 1 minus x minus 3 cubed. Now I'm going to go ahead and distribute the first part to get 3x minus 3, but I'm going to leave the last part alone because when I derive the last part, I can use chain rule to do that. I mean, I don't want to have to split this up into x minus 3, x minus 3, x minus 3, and distribute all of that. Oh my gosh, that's extra work. Don't need to. Chain rule helps you derive the outside function and then times the derivative of the inside function. That's much, much faster. Okay, so let's derive this thing. So du dx, let's get the derivative of this, would be 3. The derivative of 3x is 3. The derivative of 3 is 0. So we have 3 minus, now what we're going to do is we're going to do the chain rule of this. To do the chain rule, we're thinking of this as like u to the third power, where u is that function of x minus 3 on the inside. So to do that, we're going to get the derivative of u to the third power is 3u squared times the derivative of what's inside, which would be du. Okay, so that's how we do chain rules. The derivative of the outside function, hold the inside function fixed, inside, times the derivative of the inside. So this would be 3 times the quantity x minus 3 squared times the derivative of the inside function, which would just be 1. The derivative of x is 1 and the derivative of 3 is nothing. So the derivative of the inside function is just 1. Okay, so this becomes 3 times the quantity of 3, x times the quantity of x minus 3 squared. All right, now what we're going to do is we're going to set that function equal to 0. 3 equals 3 times the quantity x minus 3 squared equals 0. That's going to help us find mins and maxes. So let's do that. I'm going to go ahead and add this to both sides, and we have 3 equals 3 times x minus 3 squared. And I basically have to solve this thing for x. I want to find where x is, or determine the numerical value of x1 and x3. So I'm going to start by dividing both sides by 3, and I get 1 equals x minus 3 squared. Now at this point, I'm going to go ahead and square root both sides. And when I do that, I get 1 is equal to, plus or minus 1 is equal to x minus 3, because the square got rid of the square root. Go ahead and add 3 to both sides, and we get x is equal to 3 plus 1, and x is equal to 3 minus 1, which would be 4 and 2. Those are your values. 4 would be x3, 2 would be x1. Describe the motion of the particle if its total energy is E2 when it is at x equals x1. Well, the object will isolate about point x equals to x1. Okay, it's a typo there. Will oscillate. Okay, so the particle is going to move back and forth about point x, about this value of x1. Okay, so if we go to the graph, look at the bowl. It's a minimum. Okay? And if you think about it, if you had a marble, you'd roll the marble, it would oscillate back and forth in this thing, right? It will move to the right until its potential energy is E2, which is the point at which it momentarily comes to rest. It will go back to the left until its potential energy is E2 again. It'll go back and forth to these points forever, assuming no loss due to mechanical energy. Part C, what is the particle's speed at x equals x1? So what is the speed right there? Well, if the total energy is 40 joules, here's the deal. Total energy equals K plus U, right? Okay, we're looking for the particle's speed. You know that relates to kinetic energy. You know it's going to. So we got to figure out the kinetic energy. Well, here's what we do. Figure out the potential energy evaluated at x1. Okay, now that would be the potential energy evaluated at x. Remember, x1 was 2. Sorry, I forgot to put the units, 2 meters. So we're going to evaluate at 2 meters. We're going to x evaluated at 2 meters for the original potential energy function, which would be 3 times x minus 1 quantities minus x minus 3 cubed. And we're going to be plugging in a 2 everywhere you see an x to evaluate that. So u of 2 would be equal to 3 2 minus 1 quantity of 2 minus 1, and then quantity of 2 minus 3 to the third power. That would be 3 times 1 minus negative 1 cubed. Well, u of 2 would be 3 plus 1, which is 4 joules. So 4 joules at that particular point. Now the kinetic energy would be the total energy minus the potential energy, right? Subtract that over to the other side. And so we get 40 joules, that's the total energy, minus 4, which would be 36 joules. If we take our kinetic energy calculation and solve for speed, we would multiply by 2, divide by mass, square root. 2 times the kinetic energy over the mass would give us 2 times 36 over the mass. Were we given the mass? Let's go back and look at the problem. 2 kilograms. Well, that's nice. That cancels. That's going to leave you with 6 meters per second. Sketch a graph of the force function of x. Well, here's what I would do. If you remember the derivative of x, remember we took the derivative with respect to x. That is the 3 equals the 3 minus the minus x squared. Well, if you remember, that is equal to the force function. So, and if you look, this is also going to be a negative parabola shifted up 3 units and shifted over 3 units to the right. So normally, an upside down parabola would be right there. So what we're going to do is we're going to take that and we're going to shift it up 3 units. That would be the 3 in front, and then we're going to shift it over 3 units. Okay, and what that does, guys, is that puts it right there so that you can see that it's going through the x-intercept of x1 and x3. That corresponds to the minimum and maximum. And the peak of the force function is right there at the point of inflection when you change from concave up to concave down. Okay, and then lastly, the particle's released from rest at x equals 1/2 x1. Find its speed as it passes through x1. Okay, so we're going to use conservation of energy here. And energy initial equals energy final. So what we have is we have the energy initial would be our initial potential energy equals our final kinetic energy plus our final potential energy. So initially It's at rest at x equals 1/2 x1. Okay, so if we look at the graph, 1/2 x1 right here, it's released from rest right there. Okay, x1 was 2 meters. Okay, x1 was 2 meters right here. So 1/2 x1 would be 1 meter. Okay, that's where we're releasing it from, is the 1 meter point. So let's find out, let's evaluate a potential energy function at 1 meter, and then we're going to evaluate the potential energy function at let me see. Find it as it passes through x1 right here. Okay, so let's evaluate the function at that. So the function at x equals 1, or at at 1/2 x1, which is at 1 meter, potential energy function at 1 meter would be 3 times 1 meter minus 1, and then 1 minus 3 cubed. Well, that's going to be 3 times 0 minus -2 cubed. And then what we have there is we have -8 times negative would be +8 joules. So that's going to be 8 joules associated there. So we have 8 joules equals 1/2 mv squared plus, now we need to evaluate through x1. Okay, now where is x1? We established that x1 is at 2 meters. So 3 times 2 minus 1 minus 2 minus 3 cubed. That would be 3 times 1 minus -1 cubed. That would be 3 minus a -1, which is 4 joules. So minus 4 joules. I'm going to go ahead and subtract these 4 over here. We get 4 equals 1/2 mv squared. Go ahead and solve for speed. Square root of 2 times the 4 divided by the mass, which was 2 kilograms. Nicely cancels, square root of 4 is 2.